All right, students, I'm just going to give you a couple minutes. You can pause the screen to answer these questions on your warm-up. There are just three of them, number 5, 6, and 7. Please pay attention to number 5 with the graphs and the bars. Number 6 and 7 should be pretty easy. You have about a minute and a half to do these three questions. By now, you should have done this before we start playing the video because the video is primarily for the lesson. But number 5 says, which graph represents the relative distance between particles of most substances in their solid, liquid, and gaseous states? So we're talking about the distance between particles. You know, two of these states of matter, the particles are always touching. And in one of these states of matter, the particles are never touching unless they collide, so they're the furthest apart. So if you look at your y-axis, at the bottom is close together and at the top is further apart. If you chose graph A, I'm pretty sure you're correct, because solids would have particles close together that just vibrate. Liquids would have particles that are touching indefinite shape, but they just slide past one another. And then gases have particles that are super far apart until they collide. And this picture over here to the right really helps you see that. Number 6, the diagram above shows the matter changing state. What effect did the change in state have on the particle energy in motion? Well, pictures say 1,000 words. If I were you, I'd go ahead and label this first picture where we start a gas. That gas is changing to a liquid. So if we have a gas changing to a liquid, we would call that condensation. You need to ask yourself, would that be endo or exothermic? Are we gaining heat energy or are we losing heat energy? So the object is actually getting warmer. So we should be losing energy and the particles should be moving more slowly. That is not getting warmer, it's getting colder. So if you chose A again, you are correct. In the diagram above, which process is represented by letter B? So letter B says we are changing from a liquid to a gas. Liquid to a gas would be evaporation or vaporization. If you chose D, you are correct. So now on to our lesson. Our lesson today is going to segue from states of matter and phase changes. You should have realized that a state of matter cannot change phases unless heat is added or taken away. And that heat energy we call thermal energy back in Unit 2. So this whole little mini lesson is about thermal energy and how it affects kinetic energy as temperature changes. That means increase or decrease. Temperature is simply a measure of the average kinetic energy of particles. It can be measured in 3 different ways. Most of you are familiar with Celsius and Fahrenheit. You may not have heard of degrees Kelvin. If you look at the temperature scale to the right, degrees Kelvin is usually for extreme temperatures, things that get extremely hot, extremely cold. We'll usually use Kelvin. Most countries in the world, as you'll see through this trip presentation, use Celsius. We are one of the few countries that still use Fahrenheit. 1 Kelvin degree is the same as 1 Celsius degree. It's just a bigger scale. I'm not going to read this to you, but Lord Kelvin, it was named after him. The temperature scale, it was absolute temperature, which molecules could stop moving, or it's infinitely cold. He theorized if we reach absolute zero, if we actually could, those particles would stop moving and it would lead to a 5th state of matter. I will talk about that 5th state of matter, but you will not be tested on it. Einstein and him called that Bose-Einstein condensates. If we actually reach absolute zero, which is unachievable, then particles would totally stop moving. We have theories of what would happen to matter if that occurred, but we'll never reach that here on Earth, as far as I know. Fahrenheit. There was a guy named Fahrenheit. He lived in the Cayman Islands. He was associated with territories Puerto Rico, Guam. His name was Daniel Gabriel Fahrenheit. He was a pioneer of exact thermometry, and he laid the era of precision in thermometry by inventing that mercury thermometer that we're so used to. We'll talk about the properties of mercury, which is an element on the periodic table, and how that is used in thermometers. Anders Celsius died in 1744. He was a Swedish astronomer, physicist, and mathematician. Again, I'm not going to quiz you on these scientists, just know that those temperature scales are named after them. So back to countries. If you look here, countries that use Celsius are in gray. That's pretty much every country almost, except for a few islands over there off to the east of the Philippines, one country in Africa, I think you got over there Dominican Republic, and then you pretty much have the United States as the only main country that still uses Fahrenheit and green. Maybe we need to get with the times. Again, I'm going to recommend that you memorize certain temperatures in Fahrenheit and Celsius. Water boils at 212 degrees Fahrenheit. You need to lock that in memory. Water boils at 100 degrees Celsius. That one's easier to memorize. Your body temperature should be 98.6 degrees Fahrenheit. So if it's high or way lower than that, you have a fever. Fevers can be high or low. That would be 37 degrees Celsius. Another one I want you to memorize is water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. That freezing temperature is important in mechanics, cars, even in home ownership. You don't want your pipes to bust, so we always cover our spigots outside in freezing temperatures. So temperature, as the temperature of an object increases, the average speed in the particles in their random motion also increases. So we would say that that relationship between temperature and movement of particles is directly proportional. The temperature of a substance does not depend on how much of it you have. I'm going to say that again, put a star by that in your notes. The temperature of a substance does not depend on how much of it you have. The temperature of the tea in this cup is the same as the temperature of the tea in the entire teapot, even though there is more tea in the teapot. Thermal energy, we know, is heat energy. The kinetic energy of all particles in an object. Kinetic energy is movement. Remember, potential energy is stored energy. This depends on three things: temperature, mass, and type of substance. I'm going to say it again, put a star by that bullet point. Heat energy or thermal energy depends on temperature, mass, and type of substance. So let's see those relationships. Thermal energy will increase as temperature increases. Again, that's directly proportional. It is measured in joules. Thermal energy and mass. Let's see how those two factors are related. There's nothing to write in your notes right here. The more particles there are in a substance at a given temperature, the greater the thermal energy of the substance. So mass does affect thermal energy. If you have more of something, you have more thermal energy, even though the temperature is the same. I'll say that again. You can have more thermal energy if you have more mass of an object, or a liquid, or a gas. But the actual temperature could stay the same. Let's put that in a situation here. So let's say we have two beakers, beaker A, beaker B. So if you look at this picture, the liquid in beaker A, based on this thermometer, is 80 degrees Celsius. The temperature in beaker B is also 80 degrees Celsius. The temperature is the same. So I'm going to ask you, which one of these, though, would have more thermal energy, A or B? Think about it. If you chose B, you are correct, and the reason being is because B has more mass. Even though they're the same temperature, B has more thermal energy. Now let's take it here. We have an iceberg, and we have a cup of coffee. One has a higher temperature, one is cold. Which one has more thermal energy? If you chose the cup of coffee, you're actually sadly mistaken. That is wrong. The cup of coffee has less thermal energy even though the temperature is higher. because it has less mass. The iceberg has more thermal energy. Don't always think of thermal energy as always hot. Sometimes it could be the absence of heat, which we call coldness. So because this iceberg has way bigger mass, it has more thermal energy. The most important thing I want to teach you in this lesson is real-life examples of what is thermal expansion. Thermal expansion, or the word expansion, means an increase in the size of a substance in response to an increase in temperature. So some substances will increase in size and expand as temperature increases, and some substances will contract. That's the opposite of expansion if temperature decreases. So let's look at some of these things and how that affects everyday life. So here's an example of thermal expansion. We have 3 different containers of the same quantity of water. As temperature increases, so we'll call this one container A. It's 70 degrees. Our liquid is at this level in the container. And those particles are sliding past one another pretty slowly. If we add heat, thermal energy, and increase that temperature and double it, you can see that we almost double the volume or the amount of space that liquid takes up in container B, even though it was the same original amount of liquid. Now let's say we increase that temperature another 40 degrees. That water will build up pressure. Those particles will move faster. They will spread further apart as temperature increases. That's what we call expansion. And that will eventually lead to a pressure buildup, which will cause water to seep out or to blow off the lid of this container. I work on cars, so a good example of that is if you have thermal expansion and you put water instead of antifreeze in your vehicle, as that temperature increases on your car as it runs due to friction, that pressure could build up and it could eventually blow off a radiator hose or make your radiator actually explode because there's too much pressure buildup if we use straight water. Here's another example of thermal expansion, except it's the opposite. We're going to call it contraction. Expansion joints and bridges. So every time you drive over a bridge, if you've been riding in a car and you feel that little da-dunk, 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 every so many feet there's this joint in a bridge that is called an expansion or contraction joint. So as temperatures change in winter versus summer, we don't want the concrete or asphalt to crack as that bridge expands and contracts. Same thing with sidewalks. If you're walking out to wartime and you look down at the sidewalk, you'll notice about every 4 feet there is a cut in the concrete, and that is an expansion joint so that concrete doesn't crack. Some of your driveways don't have enough expansion joints, and you'll notice they start cracking as we go through winters and summers, winters and summers. That's through expansion and contraction. Hot air balloons. We know hot air expands, and because it expands, it becomes less dense and the hot air balloon rises. So let's keep going through a few more examples. Here are some gaps and bridges that we see. That is what your car makes that noise over every time it goes. You'll see that it has teeth that lock in, so as it expands, those gaps will close. When it contracts in colder temperatures, they'll spread apart. It won't break. I could have that backward, but sometimes the contraction can cause the breaks or the expansions. Again, I'm not going to go over it much more. Pictures say 1,000 words. We've already went over that picture. We've talked about water. Water has unique properties. As water freezes, it expands. As it boils and starts turning to a gas, it also expands. So water has very unique properties that we'll talk more about later. The last one I want to talk about is the bimetallic strip in a thermostat. So many of you have these thermostats in your house. Some are digital now, but you can slide this lever to increase the heat or temperature. But there's this coil of metal here. And as it gets cold, it'll shrink and then it'll cause there not to be contact with the metal conductors. And it will turn off or on your air conditioner or heater based on thermal expansion or contractions. The rate of that cold expansion was figured out mathematically and precise to make sure your thermostat is setting your room temperature to the appropriate degree. So you need to finish your notes. There's an enrichment activity at the end, but if you have not finished your flip book or your quizzes, You're behind. You need to finish that flip book first, and on the back of these notes, it'll say go to page 279 in the textbook, and you can do an enrichment activity. Enjoy the rest of your day.